We just found out that if we terminate a transmission line, lossless transmission line, in some arbitrary load impedance, the result would be an input impedance at the other end of the line that is likewise some complex number that's not equal to the load impedance itself. However, there are a few cases, special cases, where the relationship between the load impedance and the input impedance is interesting and important to know. And so let's look at a few of those. First of all, the most important of all the special cases. Let's say we have a load whose impedance is numerically equal to the characteristic impedance of the transmission line. So in other words, we have a load whose impedance is purely real, a real part equal to Z0, an imaginary part equal to 0, a resistor with value of Z0, characteristic impedance. Now, I'm careful here to say that the impedance is numerically equal to Z0. The load impedance just happens to have an impedance value that is numerically equal to the same number as the characteristic impedance. This doesn't imply that they are the same physical things, merely that they have the same value. This case is what we call the matched load, and I put matched in quotation marks here because this causes great confusion for students. Earlier in the class, of course, we talked much about conjugate match and the results of conjugate match. If we have a conjugate match between a source and a load, then all the available power of that source will be delivered and thus absorbed by the load. Here, when we say matched, we merely mean that the load impedance is numerically equal to the characteristic impedance of the transmission line. It says nothing about a conjugate match. We cannot infer that a conjugate match exists or does not exist. And of course, this makes sense because there's no source in the circuit. All we're doing is talking about an input impedance or load impedance. We have to have a source impedance before we can determine whether a conjugate match exists. A load by itself is not sufficient, and therefore we cannot conclude that we have a conjugate match. Again, we don't even have a complete circuit here. So don't infer that a quote matched load unquote is it implies a conjugate match or implies that all the available power of some source is going to be delivered ultimately to this load. Again, in this context, matched simply means Loser! That the value has the same numeric value as the characteristic impedance of the transmission line. So why then is this quote-unquote matched load so important? What is the result? Well, let's go through our math and see what it has to say about our matched load. If we have a load impedance that's numerically equal to the characteristic impedance of the transmission line that it terminates, we can go through and calculate the load reflection coefficient for that quote matched load. We insert ZL is equal to Z0, and right away we see the numerator is 0, and therefore the resulting gamma L, the load reflection coefficient, is 0. We go back and we look at the result for the input impedance and insert the value 0 for gamma L, and what we find is this term here becomes 1, and therefore our input impedance is numerically equal to Z0 as well. What's happened here is because gamma L is equal to 0, then there is no minus wave. And because there is no minus wave, the total voltage is simply the plus wave voltage, and the total current is simply the plus wave current, and therefore the line impedance is therefore simply equal to the characteristic impedance. And that shows up here in our math. And so we find that the input impedance of a transmission line that is terminated in a load that's numerically equal to its characteristic impedance will have an input impedance that is likewise numerically equal to Z0. Perhaps the most important thing about this result is that the input impedance will be numerically equal to Z0 regardless of the length of that transmission line. We went through, and when we have a load numerically equal to Z0, then Zn is likewise equal to Z0, and notice that is independent of what that line length is. Whether this line length is 1 centimeter or 1 kilometer, the input impedance will be numerically equal to Z0 if the load is equal to the characteristic impedance of that transmission line. Now, this result is, again, a special case. Zn is equal to Z0 only when ZL is equal to Z0, when we have, quote-unquote, the matched load. I think this is one of the reasons that students often tell me that Zn is equal to the characteristic impedance, that the input impedance is the characteristic impedance. They look through the notes and they find this equation right here. Well, gosh, this says that Zn is equal to Z0. Well, this is true only under this condition. If we have this condition, then Zn is Z0. If we don't have this condition, if ZL is any other impedance other than numerically equal to Z0, then the input impedance will not be equal to the characteristic impedance. And moreover, the input impedance under those conditions will be dependent on the length of the transmission line. So remember, this is a very special case, and we can see why it's special. It greatly simplifies our analysis of input impedance. Let's show mathematically why this result is true. As I said, if gamma L is equal to 0, which is the same statement as the load impedance numerically equal to Z0. If the load is a quote-unquote matched load, then gamma L is equal to 0 and vice versa. And from that, we know that the minus wave, the complex wave amplitude of the minus wave, V0 minus, therefore is going to be equal to 0. In other words, there is no minus wave. The only voltage that we have is plus wave voltage, because the only electromagnetic wave that exists on the transmission line is a wave propagating in the direction of increasing Z. That's really the physical interpretation, or the physical result of having a quote-unquote matched load, a load numerically equal to Z0, is that it excites no minus going wave, and therefore the total voltage is simply the plus voltage. And so the total voltage, as I said here, is the plus voltage. Likewise, the total current will simply be the plus current. There's only one electromagnetic wave propagating, and that is in the direction of increasing Z. Of course, we know that the line impedance function is the ratio of total voltage to total current. In the case of a matched load where ZL is numerically equal to Z0, the total voltage is simply the plus voltage, the total current is simply the plus current, and so the line impedance function, which is the ratio now of the plus voltage to plus current. But the ratio of V plus to I plus, we know from our analysis of the telegrapher equations, is always equal to a value called Z0. The plus going electromagnetic wave creates both a voltage, a plus voltage, and plus current. They're manifestations of the same phenomenon, and therefore they are very closely and simply related by this equation. The plus current wave current times Z0 is equal to the plus wave voltage. So in the case of a matched load, the line impedance function is simply Z0. What this is saying is that the line impedance function is a value, first of all, that's purely real. It is a value that likewise is a constant. It is the same at all values on our transmission line. So if we were to plot the line impedance function with respect to Z, so this is position Z, and we're going to plot the line impedance function at every location. For the case of a matched load, we'd find at every location the reactive part is equal to 0, and at every location the resistive part is equal to Z0. And of course, then this is why the input impedance is always going to be equal to Z0, because the line impedance function is Z0 everywhere. Wherever we trim the length of our line, wherever we decide the input to our transmission line needs to be, the input impedance there will be equal to Z0, and therefore the input impedance is numerically equal to Z0 regardless of the length of the transmission line. The matched, quote-unquote matched load is the first special case that we're going to consider. Now let's look at a different case. Let's consider a situation where our load impedance that terminates our transmission line is purely reactive. The real part of that impedance is equal to 0. So the impedance is purely inductive or capacitive, depending on the sign of XL. If that's the case, let's look at the result for the input impedance. In this case, we're going to use the input impedance form written here. It's a little bit easier to do the algebra in this case. We're going to insert for every ZL the value of JXL, XL being a real value, XL being the imaginary part of the complex number. Remember, the imaginary part of a complex number is a real value. So we place it in here. Notice we have J squared at that point, which becomes minus, and we can go through and then pull out the J in the numerator, the the square root of -1 here, and pull it out front, and we see the input impedance has this form. The interesting thing about this is that the real part of this result is equal to 0, and the imaginary part is this result back here. XL, remember, is a real value, so everything in this part is purely real, and multiply that by J, we get a purely imaginary result. In other words, if we terminate our transmission line in a reactive load, then the input impedance will be purely reactive. Now, it's going to be a different reactance than the original load reactance there. The load may be inductive, and therefore XL is positive, whereas the reactive part of Zn could be negative, or vice versa. The actual value depends on, of course, all the parameters of this result, the length of the transmission line, beta, characteristic impedance, and of course the original load impedance. So in summary, if we have a load that is purely reactive with reactance XL, the input impedance is going to be purely reactive. Notice the input reactance is different than the load reactance, and of course the value of the input reactance will depend on the length L. If we went through into the analysis of the line impedance function itself, for the case where the load is purely reactive, we inserted JXL into the line impedance function in a little algebra, we could show that it simplifies to this result. If we look closely, this result is likewise a purely imaginary impedance, in other words, a purely reactive line impedance. It depends on position. The reactance is going to change with respect to position, but at every point, the real part will be equal to 0. And this is shown plotted here. Again, the line impedance function with respect to position Z. Blue is the real part of that line impedance function, and it is 0 at every spot. The imaginary part then changes as we move down the line. And of course, it's interesting, this change there. As we go from 0, in this case, the reactance is positive and therefore inductive, and it'll actually go up to infinity, where the magnitude will become infinity. At that point, it flips to a minus infinity reactance, in other words, capacitive, and as we move back up the line, we find the impedance becomes less and less negative, and then it converges back to a value of 0. As we move further down the line, the reactance becomes positive again, and again it will increase to infinity at a point. And you can see that there's a periodicity in this line impedance function. And so the reason that the input impedance is purely reactive is because the line impedance function is purely reactive at every single point on the transmission line. Again, the input impedance of a transmission line depends simply on the length of the terminated transmission line. Wherever you cut the length of that line, whatever the line impedance value is at that location, that will become your input impedance. Cut it at different lengths and you'll get different input impedance values. Let's now consider the opposite special case of the previous one. Instead of having a load which is purely reactive, whose impedance is purely imaginary, let's consider a load that's purely real. In other words, a resistor. Now, in the last special case, we had a purely reactive load, and that led to a purely reactive input impedance. We might infer then, if we have a purely resistive load, that would lead to a purely real impedance. But that is not the case. If we have a purely resistive load, a resistor, what we find is the input impedance will have both a real and imaginary part, both a resistive and reactive component. Now, why would this be? Well, if we look at the case of a purely reactive load, think about what we're doing. We're connecting a reactive load to a transmission line, a lossless transmission line, a two-port device that is lossless. In other words, has no resistive elements in it. It's all inductance and capacitance, inductance per unit length and capacitance per unit length for a lossless transmission line. So the overall circuit then has reactive elements in the transmission line, lossless transmission line, and we connect to it then a reactive load we would only have reactive elements in the entire circuit. Since the input impedance has to comprehend the entire circuit, the transmission line that is terminated by a load, if both the load and the transmission line are nothing but reactance, then the input impedance is going to be purely reactive. Conversely, then, if we connect a resistor to our transmission line, we terminate our lossless transmission line with the resistor. Now we have a situation where even though there's no resistance in the transmission line, the lossless transmission line itself, there is a resistance in the load. And so the entire one-port device has both reactance and resistance, and therefore the input impedance, which again reflects the overall circuit, must have both a real part and an imaginary part, and generally speaking it does. More specifically, if we were to go through and look at the line impedance function that would result from a purely resistive load, we would find that it looks very much like we would get for a line impedance function where if we had an arbitrary load. Any load with a resistive component then is going to lead to a line impedance function which has both a resistive component because of the resistive part of the load and a reactive component because of the reactance of the transmission line, as well as, of course, the reactance then of the load. And so as we move along the transmission line, we see then that the line impedance function now will change with respect to position, both in terms of its real part and in terms of its imaginary part. The input impedance is just the line impedance where we decide the length the transmission line needs to be. Again, wherever we cut this length for a given load, that's where the input impedance is going to be. And clearly it is going to be an input impedance which is complex, both real and imaginary, even if we have a purely real load. Now, the one exception of this rule, of course, is if this real load happens to be numerically equal to the characteristic impedance of the transmission line, and we have our quote-unquote matched load. In that case, we find that the input impedance has an imaginary part which is equal to 0 and a real part which is equal to Z0. Essentially, in that case, we have the reactance, inductive reactance, and capacitive reactance that are canceling each other out. We sort of have a resonant situation where even though the transmission line certainly is full of reactance, the overall imaginary part is 0 because the inductive and capacitive parts essentially are in balance for that case. Let's look at one last special case, and this special case does not involve the value of the load impedance that terminates the transmission line. Instead, this special case involves the length of the transmission line, specifically the value beta L, which shows up in our complex exponentials, or from Euler's equations, our cosine and sine functions. If we have a situation, let's say, where beta L is equal to 0, or close to 0, it's very small. Either the physical length of the line is very short, or beta is very small. Remember, beta is proportional to frequency omega. So if we have a very low frequency, then beta L would be very small, even if the physical length of the transmission line were significant. At any rate, regardless, if we have a situation where beta L is very small, we find cosine beta L is approximately equal to 1 and sine beta L is approximately equal to 0, and we do our algebra and we find that the resulting input impedance is, in this case, equal to the load impedance. The input impedance is equal to load impedance when beta L is very small. And this is true regardless of the value of that load impedance. Now, this is a case that you're very familiar with. This is really the assumption that you've been using all along in your earlier circuits classes. The reason that we didn't have to worry about inductance and capacitance per unit length is because the beta L essentially of those wires, of those transmission lines, were small. And in that case, then the input impedance we get here is simply equal to ZL, whatever ZL is. And of course, this is what a freshman circuits class would tell you if you had a conducting wire here and a conducting wire here and a hunk of insulator between the two. And we said, what is the impedance if the load impedance is ZL? Well, certainly we would say that the input impedance then would be equal to that value ZL, since there'd be no impedance associated with this conducting wire or that conducting wire. The input impedance would be equal to this. And that's true, again, as long as this impedance is approximately true, as long as our frequencies are low or the physical size of our circuits are relatively small. But now that we work in radio engineering, omega is very large, and therefore beta is large, and therefore beta L is not small, and therefore we get the results that we show for the input impedance being different than the load impedance or the characteristic impedance, generally speaking. But in this special case, again, this is the low frequency case that we've really been dealing with up to now. In that case, and that case only, the input impedance happens to be equal to the load impedance, again, regardless of the value of that load impedance ZL.